Hi, this is my presentation on modeling the Big Bang. This is from NSTA 2026, and the purpose here is to bring abstract ideas down to earth with something called active models. So we are doing some modeling today. But this model is analog, so welcome to the analog 80s. Everything we're doing here today is going to be hands-on. Aside from the way that I'm delivering information and instructions through my slideshow, everything in this workshop is hands-on and screen-free. If that is not your jam, that's fine. I'm expecting a couple of folks maybe leave when I announce this part. Everything is hands-on and screen-free. But I have found that my students really appreciate breaking their eyes away from the screens every once in a while and doing something with their hands. So, my name is Amanda Libke. I am the Science Department Chair at Kerman High School in Central California. This is my 23rd year teaching secondary science. My specialty is Earth and Space Systems. I also teach physics, and in the past I taught middle school, and for the first time next year I'm going to be teaching biology. There's my email if you want to get in touch with me, and I was awarded Kerman Unified Educator of the Year for last year, 2024 to 2025. So, some background information. Now, I'm going to just sort of speed run through what my students would take days to go over on their own. So we're really focusing on ESS 1-2, high school ESS 1-2 here. We're trying to understand the Big Bang based on 3 specific lines of evidence. And as we go through this modeling activity, we're going to hit on all 3 types of, or all 3 pieces of evidence here. So, we're going to start with, starting with the composition of matter in the universe. So we know that the universe is about 75% hydrogen and 25% helium. And I decided to impart this information through stories. I love stories. In fact, if I have a second presentation going on at NSTA 2026 on turning your slide decks into stories. So like all good stories, this one starts once upon a time with this young woman named Cecilia Payne. She was looking at stellar spectra at Harvard University in the 1920s, and she discovered that the spectra of stars show you what the star is made from, and that most of the universe's mass is found in stars, and that most of that mass is hydrogen, with a little bit of it being helium. Heavier stuff like oxygen comes from the insides of big stars that have died in a supernova. Now, I use the word died, but of course it is put in quotation marks because stars are not actually living. The universe isn't old enough yet for stars to go supernova enough to have a bunch of heavy elements. So this key takeaway here is that the universe is young and is made of light elements. So that is one piece of evidence. The second piece of evidence that I want to talk about is CMBR, cosmic microwave background radiation. And this is one of my favorite story times. Once upon a time, we had once upon a time meaning the 1960s, 2 young scientists named Arno Penzias and Robert Wilson were looking into deep space. Again, it's in quotation marks because these guys were actually using a radio telescope to do this. They kept picking up a background hiss that really annoyed them. They thought that it was maybe the telescope wasn't set up right. Maybe there was pigeon poop inside the Horn telescopes. Basically, whenever you see these guys on the internet, they're shown like what you see over there on the right. Just a couple of angry scientists from the 1960s with a bucket and a broom and a mop trying to get rid of the pigeon poop. At the same time that they were hearing this, there was another scientist by the name of Robert Dickey over in Princeton who predicted that if the Big Bang was real, then there should be some leftover energy from it. There should be some way stretched out energy waves in the form of microwaves still floating around in space. This explained the hiss that Penzias and Wilson had found, and they found it on accident. They named this cosmic microwave background radiation, or sometimes just CMB or CMBR, and they received the Nobel Prize for this in 1978, even though they weren't really looking for it directly. This was an accidental Nobel Prize. Key takeaways: CMBR shows that there was a big explosion of energy in the universe's past. So far we know that the universe is young. We know what it's made of. It's not old enough to be made of heavy stuff. And we know that there was a big explosion of energy in the past because we can still detect the stretched out energy waves as microwaves today. Last line of evidence comes from the motion of distant galaxies, and this is redshift. So our last scientist story is going to be Edwin Hubble. I made that GIF. It took me forever, but I could not find an animated GIF online that I liked enough to actually get the point across. So I made that GIF using all kinds of weird text on PowerPoint. In the 1920s, astronomers, not just Hubble, I gotta look up his name, Vesto something, Vesto Slifer? Yeah. I'm not having a stroke. Listen, there was a few scientists, and I think the guy's name was Vesto Slifer, who noticed that nearly all galaxies are redshifted. But Slifer didn't really do anything with this. This meant that all the galaxies are moving away from the Earth, but it was Edwin Hubble that noticed that the galaxies that were the furthest away are more redshifted, meaning that they're moving away faster than the galaxies that are close to Earth. This eventually became known as Hubble's law, and this shows that the universe is expanding today, which means that if you go on rewind, and sometimes I have to explain what that means to my students, if you put the whole thing into reverse, you are going to eventually get to the universe's starting point, a teeny tiny point called a singularity. Key takeaway, this proves that the universe is expanding. Now, it would take a few days for students to go over all of that information, notes and discussion and activities and drawings and whatever. The model that we're making today is completed within one class period. But there is an extra component that we are doing along with them. So now let's go and make our model. There are 3 parts that we're going to complete all at the same time. First off, a diagram of universe expansion. You have a blank copy in your handouts. You'll be using this. My students draw this by hand. They just go for it in a notebook. And they do this activity, the actual diagram, over a couple of days before we put together the model. So this is like maybe 2 weeks worth of information leading up to actually making our model. This diagram is very loosely based on the introduction to Neil deGrasse Tyson's book, Astrophysics for People in a Hurry. Highly recommend it. It is a fantastic book, but it is some advanced stuff, and I teach this topic to freshmen. So I did have to bring it down to their level significantly. I'm telling you that ahead of time so that you don't get grumpy as I start to talk about universe expansion and I get things maybe a little too simplistic, or I don't explain things as thoroughly as I could have. I am hitting the standard. That's what's important. Well, it's not really what's massively important. It is important. I'm hitting the standard here. I'm hitting all 3 parts of the standard in a way that freshman brains will understand. However, I do highly suggest this book if you're looking for something new to read. We have the actual universe model. You are going to need white paper and black paper. There are boxes out. Each box has enough supplies for 4 people to make a model. There's enough supplies here for 40 models. You're going to need 1 piece of white paper and 1 piece of black paper. The black paper is larger. Pair of scissors. You need a red, yellow, and blue marker, some tape, and a sheet of star stickers. And you also have this handout on the back of your universe diagram that I would like for you to use to organize your thoughts as we go through this workshop. On the left-hand side, you see what I would give my students at the end of making this model. So how is this model like the Big Bang in the modern universe? How is the model not like or unlike the Big Bang in the modern universe? That is yours to use as you see fit. You are not turning this into me. I am not analyzing your thinking, but I did want to show you at least what my students would be doing with this once we're finished with the model. I'm more excited about the right-hand side. How can you use this type of active modeling in your classes? Could you use this, if you teach earth science or kinder physics or whatever, you can take this activity, just go with it. But could you take the ideas here and use it for redox reaction, use it for active transport in AP biology, use it for other abstract ideas, things that are either too big to wrap our brains around, too tiny to wrap our brains around, or just too weird to have it be within the realm of what students' worldview is like. So I'm looking forward to getting ideas from all of you on how you can use this kind of idea in your own classes. So let's start on our universe diagram. We're going to start with that singularity that we talked about earlier. This is at the beginning of time, and then we have this big whoosh that expands out until today. one of the first things that pops up into the universe is photons. Photons are one form of light, and at this point in my lessons, students already know what light waves are, but I do have to tell them about photons for the first time here. Now we're going to, start our model. So take your piece of white paper that you have and just cut it into 6 strips. That's it. Those 6 strips represent the photons that form at the beginning of the Big Bang, and this is where our model is going to begin. So we have photons now. Some of those photons are going to turn into matter, but not all of them. Some of the photons just stay as photons. So now looking at your supplies on your table, how can we show this process of turning photons into matter using what I gave you in those boxes? Well, you're going to color some of these strips yellow, but not all of them. Color 4 of these strips yellow, front and back, leaving the other 2 strips alone. So these strips are now representing photons that went from white photons to yellow matter. The color's kind of important here. And the other 2 photons are just floating around. Those are the photons that did not turn into matter. All right. So we have some photons turning into matter, and some of that matter turned into hydrogen, and some of it turned into helium. Same question. How can we use the supplies provided to show this process? And the obvious answer is that we're going to color over the yellow. We're going to color 3 of our strips blue and 1 of our strips red. The 3 blue strips represent the 75% of matter that is hydrogen, and the 1 red strip now represents the 25% of the universe's matter that is helium. All right, so now we have hydrogen and helium, and that hydrogen and helium 75% hydrogen and 25% helium is trapped inside of stars. Most of it is trapped inside of stars. So to show this process with our provided supplies, we are going to start by decorating our hydrogen and helium strips with star stickers. So you've got a whole sheet of star stickers, 1 per person. Just go to town, front and back of your strips with stars. This is going to show that the matter, the hydrogen and helium, are trapped inside of stars. But remember, don't put anything on the photons. The photons are still just hanging out. They're still just vibing in the background there. Then we're going to take our matter strips, our hydrogens and heliums, and link them together to make a star. So now we have hydrogen and helium linked together to make a star. This shows that matter is trapped inside of stars in the appropriate percentage. We have 75% hydrogen, 25% helium, and we still have photons floating around on the outside that are not yet part of our system. Now that we have matter trapped inside of stars, for the first time we have darkness in the universe. Up until this point, the darkness kind of looked like a glowing fog. It'd be like the inside of a star, essentially. It would have been a glowing fog. We wouldn't have had darkness quite yet. So to represent that darkness, take your big piece of black paper and cut it up into 12 strips. Those 12 strips are going to represent the darkness of space that will form in between the stars and the photons and eventually the galaxy that we're going to make out of our model. All right, here we are. We still have leftover photons today, and those leftover photons make up cosmic microwave background radiation, and they are outside and separate from the stars. So you are going to connect your leftover photon strips to your star using strips of black paper. So the photons are there. You put a strip of black paper at the end of your star, then a photon, and then another strip of black paper. This is going to show that the photons are independent of the stars and zipping around separately from the stars. You now have a model that shows matter trapped in stars and leftover energy in the form of photons. How can we take our models and turn them into a galaxy? Well, we sure do have a lot of black strips left over, don't we? Let's use some of those leftover black strips to make one long chain at your table. Or how I'm recording this before the conference. I don't know how you're going to be sitting. But with people around you, make one long chain to make a galaxy. So use some of those leftover black strips to make a galaxy. I made a spiral galaxy. Get it? Spiral? Yeah. And congratulations, you've made a galaxy at your table. Now, what can we do to turn that galaxy into a universe? To turn your galaxy into a universe, you want to connect all of the paper chains in the entire room with all of the remaining black strips of paper, it's going to end up looking something like this. Please use all of the black strips of paper to indicate that everything we know is in the universe. There's nothing outside of it. Now, that picture right there in the background is the universe model that is hanging up in my classroom. This is my student work. That will stay up. It's pretty close to the ceiling, so it will stay up for as long as the fire marshal doesn't get me in trouble. Once someone comes in and say, that's not up to fire code, I'll take it down. But in the meantime, it's been up there since October, which makes me happy. We now have a model of the universe. Congratulations. You've made a model of the universe and you've shown how it formed all at the same time. But we forgot something. Think back to our standard. What did we forget to show? We showed composition. We showed that a few times, 75% hydrogen and 25% helium. We showed the leftover CMBR, the cosmic microwave background radiation that indicates that something big happened a long time ago in the universe's past. What we did not show, though, was redshift. So how can we show redshift and universe expansion with our model? Well, depending on how many people I have in the room when I get to this point, what we're going to do is we're going to connect the two ends of the universe to make a big loop. And then hopefully it'll be big enough to put 3 or 4 people back to back with the universe on the outside, and we will slowly walk out to show redshift, to show the universe is expanding. That's what I hope to do at the end of this model. And let's take a look at what you thought of while we were going through this. So again, the left-hand side, that is what I would have my students do. Check for understanding. If you want to share out some thoughts, I won't stop you. But this is more me showing you, teacher to teacher, how I would finish up this activity. I'm more interested in what you put on the right-hand side. So hopefully you came up with some ideas that you can share out with the people around you. How can you use this type of active modeling, this analog, paper and tape type of activity to bring some of your own abstract ideas down to earth? Everything that I used for this activity and this model, I got from my supply center. It's just paper and tape and scissors and star stickers. Everything came from the supply center. I didn't have to order anything special at all for this. Hopefully we'll have some ideas to share out at the end of this activity. Thank you so much for going on this modeling journey with me. That QR code is for the workshop evaluation, and this is my link to my resources. This tiny URL right here will take you to my Earth Science, my Earth and Space class website, where I have added a tab specifically for NSTA. That tab will stay active for a couple of weeks, and then I'll probably take it off of the navigation bar just because it's something that might confuse my freshmen. They're 15. You know, their brains are still developing. But if you go there, you're going to find the video that I'm making right now. You'll find the handout. I will post my presentation slideshow directly to the NSTA website because it is on PowerPoint, and I can't link that directly easily onto a Google Sites that I use for my classes. You'll also find some student examples of some student work, as well as information from the other presentation that I'm giving this week. Thank you so much for your focus and your attention, and if you have any questions, feel free to email me.